One of the things, hey guys, one of the things I'm hoping to be able to roll through with you guys on this, and we were able to knock it out today in the first hour, is that normally this first 6.1, there's just a couple of exponent rules that we look at, and it usually only takes 15 minutes or so to get through, and that gives me time to start something in 6.2, which is kind of a big deal. And we'll get into that today as well. Tomorrow we will do some rough sketch graphing out of 6.2, along with a little bit more of this synthetic stuff that we work with. Monday we'll put it on, we'll do a little bit more. Then I'm looking Tuesday we will be doing adding, subtracting polynomials. Wednesday will be multiplying and dividing. Friday is the halving, which I forgot what I have. And then we just continue on and on and on. The idea here is to start is that we've got, well, I was counting it. We have roughly 37, 38 school days before the end of the semester. Not that, it's really not that many. When we start marking through the days off and stuff like that, and half days and Christmas or Thanksgiving and all that stuff. So we've got about, guys, I've got about 18 or so sections left to go, total between 3 chapters. Some of them they kind of blend together and all that, and then backing into the reviews and all that. So we're going to cut it close, but as I start pacing it out, we've got about 2 days of breather. Yeah, what's not to do with review, but there's selection time for review and stuff. But we've got a little breather, but not much. We got it. The whole shift of moving stuff from to the moving the finals up before break, it actually cut about 2 days of instruction versus second semester. I think first semester is technically 2 days shorter than second when you go through full day stuff. Like, whatever. Properties of exponents. What I always like, I found out that most of you guys knew this stuff. What I always like to do is some really easy numerical values first, and then introduce you guys or reintroduce you guys to some of the rules and properties. For example, what's 2 to the first power? 2. Good. What's 2 squared? Okay. 2 cubed. 2 to the 5th. Make sure you're paying attention. Okay, and so on and so on and so on. Now, what about this? What's 2 to the 0? Good. 2 to the negative 1. Very good. It's 1/2. Inverse. Okay. Now what about this? 1/4. Very good. Is it an actual thing? Yeah. And so on and so on. So if I do this, and I'm just kind of leaving it really, really simple with 2s, and I think, do you guys know the difference between a base and an exponent? No. All right. Which of those? If I look at this, and I say 2 to the 3rd, what's the base and what's the exponent? 2 is the base, 3 is the exponent. So when you have something with the same base, and you're going to multiply it together, what's 2 to the 8th times 2 to the 4th? 2 to the 8th. I'm sorry, 2 to the 3rd. 2 to the 3rd times 2 to the 5th. It's 32, which is 2 to the 5th. Very good. Now, when you have same base, different exponents, the rule was you just add the exponents. I don't know if you guys remember that. Okay. Because when you have exponent stuff, remember what it represents. The number of times you're multiplying it together. And so on and so on and so on. That's where all that stuff came from. It might have been a couple of years since you've seen it, but as we get into it, most of this should ring a bell. Same idea. If I have 2 squared, and I raise that to the 4th, that was something what you'd have, think of it this way, it's 2 squared times 2 squared times 2 squared times 2 squared. Remember, you raise something to the 4th power, you're multiplying by itself 4 times. You break it out that way. And you would multiply. This would be 2 to the 8th. 5th is 32, 6th is 64, 7th is 128, 8th is 256. And so on. So what we're going to look at today are a whole bunch of properties. I'm going to use X for my base, M's and N's for my exponents. I'm going to list out a bunch of rules today. Same. I'll write it out. I'll write it out. When it's a long proof, but I'll show you how it goes. It's really simple to work through. Same base, different exponents when you're multiplying. All you gotta do is add. Same base or base to an exponent to an exponent. In other words, power to power. This sounds cool. Not really. Multiply it. Any exponent that is negative is not happy in its current location. So if you're not happy in your current location, you would move. So if it's not happy in the numerator, where would it be happy? In the denominator. Which also means if it's unhappy in the denominator, where is it happy? In the numerator. And then this also works with distributive property. If I have two things being raised to a power, first of all, are those two things being multiplied or added together? Multiplied. We're dealing today, guys, with what are called monomials. The monomials are a bunch of numbers put together without addition or subtraction. It's just constants multiplied by variables and so on and so on and so on. So when that happens, you basically are distributing your exponent to both pieces. It works the same way if it's a fraction. Again, you just kind of distribute the exponents to both parts, both the numerator and denominator. There'll be a lot of little subtleties we'll look at as we go along. And again, anything raised to the 0 power is always 1. The reason that happens is if you're going up and down through the number line, if you're going up the number line, you're multiplying it by 2. As you're going the other way, you're dividing it by 2. As your exponents are increasing, as the exponents are decreasing, you're dividing it by 2. What is 2 divided by 2? It's 1. So anything divided by itself is always 1. That's why this works. And then as it goes again, if you divide it 1 by 2, you get 1/2, and so on and so on and so on. Does that make sense? That's why that works, and it works for anything. Okay. All right. That's what we're looking at. So take a second. Do those two. Simplify them. There is a subtle, that didn't show up as very clean as I wanted to. There is a subtle trick when you have numbers and variables all mixed together. My what I would suggest to do is take care of numbers first, if possible, and then just work through your order of operations. I want you guys to take a second and simplify those. And as we do a couple of these, it winds up being the same thing over and over and over again. And then just go piece by piece. Okay. And I'll walk you through the first one as we're writing it down. We have negative 3xy divided by 9x to the third y to the negative 4. As I'm looking at that problem, or as I'm writing it down, the first thing I should recognize that I've got two constants, negative 3 and a 9. Can that fraction be simplified? What do you get? Negative 1/3, okay? And you're on the right track. I always like to take care of numbers first and just work my way through it. So I know that I'm going to have a fraction with a negative 1 and a 3. Oh, we didn't do this one yet. Let's go back to division. We haven't done division. Sorry, I got ahead of myself. Division. I'm sorry. I got super excited about simplifying and forgot about division. It's really, really easy. I know. You're right, it is kind of like a game. You ever play the game War? What do I gain?
Is that a 13 or
amusement? This is a 13. So 13 and S. It's a 5. Your eyes check. So have you guys ever played the game War? Okay. Really? Really? So for those of us that have never played the game War, so great. Yeah. So for in case you've never played the game before, it's basically it's okay. No one's gonna get hurt. All right, you ready? Flip it over. You win. Well, let's say aces are high. Are you ready? I win. You win. You win. You win. You win. I win. I win. You win. Anyway, so war is basically high card. Okay? War is just high card. So in between a 13 and a 5, who wins? 13. What's 13 minus 5? What happens here when you're simplifying variables via division, you're playing war. Who wins? Okay? Who wins? Same idea if it's in the denominator. In this case here, who wins this one? Denominator. So whichever one wins, you subtract the other number from it. So what's 15 minus 7? 8. Now here's the deal. It's y to the 8th is in the denominator. What's now in the numerator? 1. That y value in the denominator is not wearing a flotation device. It did not wear its vest to school. I was just going to throw a Marty McFly joke in there, but it's okay. You guys know who that is? Okay. When in Back to the Future, when he went to the back to the past, they're like, "Why are you wearing a life vest?" Anyway, so back to this one. When we have x over x to the third, what's the exponent of the x in the numerator? So what is it? 1. If there isn't an exponent there, it's a 1. So who wins, a 1 or a 3? A 3. So what goes to the denominator? Okay. Now the y was already here. This y is unhappy, so where should it go? To the top. you have y, and y to the fourth, which means your final answer would be negative 1y to the fifth over 3x squared. There is no x. This was a y. This was the y that was here. Sorry, that. Yes, ma'am. I usually put the negative one just because it's my mind. It's easier. Same thing on the next one. Guys, we got a lot to get through. You guys are running out of time. Same thing on the next one. In this case, I cannot take care of the numbers first because it's grouped within parentheses. Okay? So that means I have to take care of that first exponent. When I square the quantity 3x, what do you get? 9x squared. So you get, this one becomes 9x squared in the numerator over 6x to the fifth. Now you can simplify. What's 9 over 6 simplified to be? 3 halves, very good. And then, once again, who wins in the game of war? 5 or 2. It's the easiest way to do it. A lot of textbooks usually just say subtract the top from the bottom always and then worry about negatives. I don't like to do that. I like to just reference play war because then it'll always go, it'll always go to where it's supposed to win. Okay? It'll always deal with that. So these are the real simple ones, which means sometimes you get some funky ones. Sometimes you get stuff that looks like that. You have x squared times z to the fourth times negative 2x squared y to the negative 1, that's all in the numerator, divided by the quantity negative x to the fourth all raised to the third, or negative x to the fourth quantity raised to the third. So this one just looks kind of weird to start out with, but just like I've said in the past, start with numbers. Before I go too far, the only number right now that I can move around is what? The negative 2. Okay? Since the negative 2 is the only thing I can really move around as of right now because the other stuff's grouped in the parentheses, what I'm going to do is just write out, I know I have a fraction, I'll put a negative 2 here. Now I'm going to go variable by variable from the numerator. I have an x squared and an x squared in the numerator. That makes it how much in the numerator? X to the fourth, okay? Now I'm going to cross off the things that I've taken care of. Now I have z to the fourth, that stays. But what do I do with that y to the negative 1? Go to the denominator, good. I just leave it as y. Okay? I have to put it to the first and second. Now inside that parentheses, I have to raise all that stuff to the third power. What's the coefficient of the x to the fourth? Negative 1. So that means that this is negative 1 to the third times x to the fourth to the third. What's negative 1 times negative 1 times negative 1? Negative 1. 1 or x to the fourth to the third. Good. X to the 12. Sometimes you have to go bit by bit. All right. What's negative 2 divided by negative 1? 2. So this is going to equal 2 in the numerator. What is x to the fourth over x to the 12th? 1 over x to the 8th. So I'm just going to put x to the 8th in the denominator. The z can stay, and the y can stay. it takes a minute to go through them, but in the grand scheme of things, it shouldn't be that bad. We're not dealing with negative, we're not dealing with fractional exponents yet. What's that? That's okay. It's the same property, same rules, same everything else. Just adding, subtracting. What'd you make? Oh, you said here. You said something. Guys. No, because that negative is the value in front. If it was written like this, that's it. That'd be x to the fourth times negative 1. Because then you're dealing with for the x to the fourth. Yeah, but if it's an even number, if it's positive. All right. So there's that. Let's talk about polynomials now. Ladies and gentlemen, enough. You guys are way too much today. Okay. Polynomials. Polynomials are a whole bunch of monomials put together via addition or subtraction. Polynomials have what are called nth degrees. An nth degree polynomial for example, real something simple. An nth degree polynomial like 3x to the fifth plus 2x cubed minus 4x squared plus plus x minus 4. That's an nth degree polynomial. What is the degree of that polynomial? Very good. It's a fifth degree polynomial. The reason that it's a fifth degree polynomial is because that's the highest exponent that it has. Nth degree polynomials are written, this is a fifth degree polynomial. They're always written in a descending order. I don't know if you guys remember when you guys did ascending and descending with polynomial stuff a long time ago. I have no idea why they taught you to do ascending. No one ever uses it. We're always going to use a descending order. If you have an nth degree polynomial, you will always have n plus 1 terms in the polynomial. So if this is a fifth degree polynomial, that means I should have 6 parts to it. Fifth degree, fourth degree, third degree, squared, first degree, and a constant. That's what it means by going descending order with terms. In this case, I have a fifth degree, third degree, second, first, and a constant. What am I missing? The fourth degree. They don't normally, sometimes they don't put that in, but eventually I'm going to show you guys what we're going to need to learn to do. We're going to learn how to put a placeholder in. So polynomials, if it's an nth degree polynomial, it just means whatever the highest power is, you will always have n plus 1 terms in the polynomial. You will have n possible zeros. So a fifth degree polynomial can have how many zeros? 5. A sixth degree polynomial can have how many zeros? A third degree polynomial can have how many zeros? 3. Okay. There's a lot that's going to happen here with polynomials, and this is kind of a little bit of the start. I'm not going to get too far into this one because I don't want to worry about graphs yet. We'll do that tomorrow. All right. Now, one of the things you guys all learned how to do was taking this polynomial. Let me just bring this along. And you guys learned many, many, many years ago what's called direct substitution. You guys remember that? I ask you what is f of 3, what would you do? Put 3 in for x. Direct substitution means put 3 in for x, or x equals 3. And you would put that in the calculator, press a whole bunch of buttons, and go on your merry way. Okay? You do 3 times the quantity, 3 to the 5th, plus 2 times the quantity, 3 cubed, minus 4 times the quantity, 3 squared, plus 3 minus 4. And you press a whole bunch of buttons. Plus 2 times 81 minus 36 plus 3 minus 4. I got 854. Anybody else? Yeah, that's what I'm trying to get you to look at me. It takes time to do this stuff. Right? You're just substituting in values. You're just putting values in to figure out what you get. Would I say 800? Thank you. All right. That's what you guys did, what was called direct substitution. Excuse me, direct substitution. Well, there's actually other ways to do this. So let's take this, again, another one. I'm going to use direct substitution with a small, a fourth degree polynomial, and do that again. A fourth degree polynomial should have how many terms in it? 5. It should have 5 parts to it. A fourth degree polynomial can have how many zeros to it? 4. Right? A second degree polynomial has how many zeros? 2. What's an example of a second degree polynomial? Quadratic. So when you factor quadratics, you got 2 terms that generated zeros. X to the 4th, x cubed, x squared, x piece. Right. This, your terms are 4th, 3rd, 2nd, 1st, constant. So if I throw this one in, if you do all that one, you get 81 times 2 is 162. 162 minus 72 is 90. 90 plus 105, or 90 plus 15 is 105. Subtract 8, you get 7. You get 98. All right? Pressing a whole bunch of buttons. What if I told you there was an easier method? It slices, it dices. Okay. There's something called synthetic substitution. Synthetic substitution. Synthetic substitution is going to become your best friend over the course of the next couple of weeks. I'm absolutely positive. It is a process to substitute in values to generate solutions. It is a very simple process. So I'm going to go back to this original polynomial, and I'm going to rewrite it now with placeholders. What I mean by that is anywhere I don't have some degree, in this case it's missing which degree? The third. I'm going to put a 0. So I'm going to rewrite this as 2x to the 4th plus 0x cubed minus 8x squared plus 5x minus 7. I'm taking my 4th degree polynomial and I'm writing out all 5 terms. The terms in this case are each individual monomial that created the polynomial. Hence the Greek term poly means many, many nomials, many terms. Now we're going to do something crazy. Draw that. Okay. a minute. What are the coefficients of your polynomial? 2, 0, -8, 5, and -7. All right, so far so good. What did we just substitute in? What was it? 3? Okay. Whatever number we're going to substitute in, I'm going to put out here. And I'm going to use this little trick called synthetic substitution or synthetic division here we'll get to in a minute. Same thing. This is a process. And this process is exactly the same each and every time. The very first thing you do, drop that number here. Drop your first term all the way underneath that bar. What's 3 times 2? Put that 6 here. What's 0 plus 6? Put that 6 here. What's 3 times 6? You multiply on the outside, you add in the middle. Multiply the outside, add in the middle. What's -8 plus 18? 10. What's 3 times 10? What's 30 plus 5? What's 35 times 3? Well, better yet, if you can't do that in your head, what's double 30? Yeah, if you can't do that in your head, just double 35, you get 70. Add 35 to it. You get 105. What's -7 and 105?
Oh my God.
3 times 3. Okay. There's a reason. There's a really big reason why we learned this method of substitution, because it's going to be a way for us to factor. The idea here is, let me put it this way. What is, we'll do it other ways here in a second, but what is 18 divided by 3? 6. So that means that 3 is a factor of 18. You guys okay with that? What is 18 divided by 5? 3 and change, isn't it? Not a whole number, which therefore means that 5 is not a factor of 18. All right. Now, no, that's backwards. Sorry. Let me ask you this. What times what is positive 8 that you add together to get -6? -4, -2. You guys okay with that? So, if I set these equal to 0, what are your 2 zeros? Okay. What are the coefficients? 1. I put a 4 here. What would I do first? 1 times 4. What's -6 plus 4? What's 4 times -2? That means 4 was a factor of the term x squared minus 6x plus 8, which means if 4 is a factor, it means it's a 0. If the 0 is 4, the term is x minus 4. This is how we're going to be able to factor big polynomials. It's a term. It's a 0. We'll come back to it. I'm just showing you. Showing you where we're coming to. Okay. Don't worry too much about that one. Just showing you why we do this, because eventually we'll be able to factor out large polynomials knowing zeros. All right, let's do this again. Synthetic substitution. I got a fifth degree polynomial. If I have a fifth degree polynomial, how many terms should I have? Good, you should have 6 of them. So I have f of x equals negative x to the fifth minus 4x cubed plus 6x squared minus x. And I'm going to use synthetic substitution for x equaling -2. So when I start writing out my little sideways L thingy-majiggy, I use my coefficients, but I have to have placeholders. Fifth degree, I have my coefficient is -1. What's the coefficient of the fourth degree? 0, because there's nothing there. What is the coefficient of the third degree? -4. Second degree, first degree, and the constant. And what are you synthetically substituting by? What's your first step? The -1. What's -2 times -1? 0 plus 2? 2 times -2. -4 and -4. -8 times 2. 16 and 6. The answer is 90. Yep. When you substitute in a value, fifth degree. Okay, the fifth degree polynomial means that that's the highest degree of the polynomial. So the book is nice. They usually write everything in descending order for you. If you have a fifth degree polynomial, you should have 6 pieces to it. Fifth degree, fourth degree, third degree, squared, first degree, constant. In this case, it only had 5, 3, 2, and a single, which means you had to have placeholders. The placeholders go where they're needed. You needed a fourth, you needed a constant. That's how we got 6. Does that help? All right. Okay. Thank you. Okay. Actually, all you have to do for when we're doing synthetic substitution, see what I did? I just circled it. I'm fine. Because, yes, 90. Your answer is 90. The idea here is it's just practicing this process for now. Because eventually we'll start to learn how do you come up with what you're going to divide by and things like that. Yes, ma'am. F of x, x is a function. It's a function of x. Yeah, it just means f of x. It just means this is a function of x. It means you know how you pass the function test for every input of x, there exists exactly one y value. It just means that it is actually a function versus not a function. All right. Same idea. You have 3 on the outside. Third degree polynomial means how many terms should you have? 4. One more. Okay. Pull your coefficients out, -3, 7, -4, and 8. Multiply on the bottoms, you add in the middle, but you drop the first term. Synthetic substitution, as you get going on this, it is ridiculously fast. Because it's just adding and multiplying, okay? More often than not, as we get into like the weird polynomial stuff later on, your numbers are going to be a lot cleaner because the weird things will happen. I'm not going to get to that, but it gets a lot cleaner with the numbers in the middle and stuff. Okay, so you wouldn't have to worry about 7 times 35. That would just be that. Okay. I believe, did I post the problems yet? I don't remember if I did or not. And I don't remember. I just don't remember which ones they were. Do those, please. 6.1 and 6.2. I got 6 of those monomial simplifyings, and then 6 of the synthetic substitution stuff. PDF files are up there, so you can use those right away. We'll be doing the same stuff. Well, we won't be doing a lot of the exponent rules tomorrow, but we're doing more of the synthetic stuff tomorrow, along with graphing. Yes, ma'am. Huh? I have a degree in math, so I don't know. He failed English. That's impossible.
Yeah, well,